would likely want to adjust in this case. Let's look at a kind of a crazier one. So here, there is no such thing as a treatment effect. So for the red group, the line looks like that, and for the blue group, the line looks like that. So you couldn't call that the treatment effect because, like right around here, the treatment effect is 0, or right around there. So this is an example of interaction. The treatment effect depends on what particular value of x that you're at. So there's both a difference in intercepts between the two lines and a difference in slopes. So that's just an instance where you don't even have the idea of a treatment effect. Doesn't make any sense. The treatment effect depends on what value of x you have. And in fact, it even reverses itself. Okay, so here's another simulation. I wanted to do an example of kind of continuous adjustment. So here's my y, and here I have my x1, and x2 is the color coding of the points right here. So kind of, I think, lighter meaning higher values and darker meaning lower values. Okay, so this is actually a different set of data. I'm just rerunning the simulation each time. But let's actually do the 3D plot instead of the 2D plot. And there it is in RGL. And you can see that there's this strong relationship between y and x2, and then this kind of less clear relationship between x1 and y, and that's the kind of noisy regression line that we saw from the previous page. So, but what happens if we, instead of plotting y versus x1, we plot the residual of y having taken out the effect of x2, and the residual of x1 having taken out the effect of x2? There's almost no variation left, right? So y and x are almost perfectly explained. At any rate, the point of this example was just to give you an example where, in this case, x1 was unrelated to x2, x2 was strongly related to y, but the adjusted relationship between x1 and y was largely unchanged by considering x2, which makes sense given that first point. The magnitude of the slope changes. However, the residual variability is changed dramatically by considering this other variable. So I think in summary, let me summarize these final thoughts. Modeling multivariate relationships is difficult if you want to interpret them. If you just want good prediction, then there's strategies, kind of automated strategies you can follow. But if you want to interpret these results, if you want to interpret these regression lines, the practice of adjustment can have a profound effect on your variable of interest. And so I would just encourage you to kind of play around with simulations like these to see how you can get the inclusion or exclusion of another variable to change analyses. So the discussion from these analyses deals with the impact of inclusion or exclusion of variables on associations. But an even harder problem is ascertaining whether kind of x causes y. So that, in addition to all of these considerations, adds this secondary consideration. And so that's another problem. That's kind of a hard problem. That's the so-called domain of causal inference. But for our purposes here, we want to kind of mostly understand how and why the inclusion of variables changes the relationship between a variable of interest and the outcome in a regression model. And I think these examples show you that you can get very different answers depending on how you, depending on what variables that you include.